The field of astronomy offers a wide range of opportunities for engaging students in physics. Optical astronomy, however, requires nighttime conditions and reasonably low levels of light pollution. As a result, many courses resort to teaching about astronomy rather than teaching by doing astronomy. This paper presents some ways in which hands-on activities related to astronomy can be developed to physics and science lessons and STEM clubs during the school day. A good starting point is an investigation of the path of the Sun using a simple pole mounted vertically in an open, unshaded location. Mark the tip of the shadow once an hour to observe the change in length and direction of the shadow over the day. Marking the shadow tip at midday on a regular basis, perhaps once a week for a term, will show how the maximum angle of the Sun changes over time. By continuing the process over the whole year, the complete annual cycle will be recorded. These practical activities can be followed up in the classroom using the free astronomy program Stellarium. This can be used to show the motion of the Sun throughout each day and to highlight the seasonal variation. Students' knowledge of the Sun's relative motion through the sky can be further developed through using and designing a sundial. Creating a working sundial involves finding the local meridian line, taking account of the time of year, and following a process of accurate calibration. A good starting point is the equatorial sundial, easily made from stiff card. A common design for permanent display outside is the horizontal sundial, which uses the shadow cast by a vertical gnomon. More elaborate and challenging designs include the vertical sundial and the classic and elegant armillary sphere. Of special note is the analemmatic sundial, which can be permanently set out in the school grounds. The observer acts as the gnomon, standing on a central plate at the correct position for the time of year and casting their shadow onto the hour markers. Projecting an image of the Sun onto a screen leads to an exploration of the physics of light and optics. Binoculars can be used to project an image of the Sun onto a white card. A small telescope can be used in this way, particularly one which has a lens cap with a smaller aperture to minimize the heat entering the system. A sun spotter can be bought or made to allow safe viewing of the Sun, while a commercially manufactured solar filter used under strict supervision will allow indirect observation of the Sun to view sunspots, eclipses and transits. If a clear projected image of the Sun can be obtained, any sunspots currently on the Sun's surface will be clearly visible. Measurement of the changing position of sunspots from day to day can be used to calculate the period of rotation of the Sun. An easy way to collect suitable images is to visit NASA's SOHO observatory, which offers images of the Sun as a movie sequence. Electromagnetic radiation and charged particles emitted from the Sun regularly interact with the Earth's atmosphere and can seriously affect radio transmissions and possibly damage orbiting satellites. This area, known as space weather, can be understood by school students and actively pursued using readily available equipment. Weather balloons or radiosondes are released every day from around the world to provide information about the troposphere, the lowest level of the Earth's atmosphere. They can be monitored via a website or tracked using a simple radio receiver. The data can be captured for analysis using free software. Simple radio monitors are available which can highlight changes in the Earth's ionosphere due to coronal mass emissions when charged particles are ejected from the Sun. This graph shows the characteristic shark's fin as the propagation of a very low frequency radio signal is disturbed as a result of a sudden ionic disturbance, or SID. Meteors passing through the upper atmosphere leave a trail of ionized atoms. Such trails reflect terrestrial radio signals, and these can be detected and recorded with simple equipment. Meteors can be detected every day around the world, and the significant peaks associated with annual meteor showers can be recorded and analyzed. A great alternative to optical astronomy is the growing field of radio astronomy. The power and relatively low cost of modern electronics can be harnessed to enable students to receive and analyze radio signals from space. A low-cost software-defined radio plugged into a USB port on a laptop computer, can be set up to receive radio signals from a variety of sources. A suitable antenna can be built from materials obtained from a hardware shop. The Sun produces radio emissions across a wide range of frequencies which can be detected using a basic antenna and radio receiver. One approach uses the drift scan method, in which the Sun passes in front of a fixed antenna to produce a characteristic graphical pattern. Interactions between Jupiter and one of its moons, Io, produces bursts of radio signals which can be detected using a simple antenna and radio receiver. The program Radio Jupiter Pro can be used to predict when radio signals might be heard. The Radio Jove project is well established and introduces students to a community of active amateur scientists. Hydrogen atoms in space exist in one of two states, with the spin of the electron and proton parallel or antiparallel. When a hydrogen atom flips from one state to the other, it emits a pulse of radio energy on a well-defined frequency around 1420 MHz. Hydrogen emissions from our own galaxy can be detected with relatively simple equipment. With guidance, students can design and build a directional horn antenna using off-the-shelf materials. This simple example was constructed from foil-coated insulating sheets for the horn, thin metal sheet for the resonant receiving cavity, and brass tubing for the antenna itself. As an alternative approach, a complete ready-built system can be purchased at modest cost to detect and analyze hydrogen line emissions from our own galaxy. Coupled with a software-defined radio, a modular low-noise amplifier and narrow filter, these simple antennas allow the collection of real-time radio astronomy data for analysis and interpretation. The radio signal is weak from a relatively small antenna even after amplification, so the signal must be averaged over 5 minutes or more so that the peak becomes visible. It's broadened because of the Doppler effect due to relative motion between the source and the receiving antenna. Final processing in Excel produces graphs like these examples of the hydrogen line emission from our own galaxy collected by my own system. Many professional astronomers now collect data from remotely controlled optical and radio telescopes. The growth of technology in this field has resulted in a range of online telescopes becoming available for public access. Some are optical telescopes, others are radio telescopes. A number of remotely operated optical telescopes can be accessed at no cost or for a modest subscription. The SLU project provides access to a set of optical telescopes and includes quests, star parties and social media groups. The Onsala Space Observatory in Sweden offers free public access to its 3 online radio telescopes. These are configured to receive the neutral hydrogen line at a frequency around 1420 MHz and can be remotely steered to any part of the sky during the day or at night. Bookings can be made at any time of day to match lesson times or STEM activities. Students can watch via a webcam as the parabolic radio telescopes move in response to their commands. Data and observations can be downloaded from a number of radio observatories around the world. Data from the Leon Moe Radio Observatory, owned and operated by the Astronomical Society of Victoria, can be streamed from their Dark Sky site outside Melbourne. Systems include Radio Jove for emissions from Jupiter, E Callisto for emissions from the Sun, a gamma radiation detector and environmental monitor, a weather station and lightning detector, a seismometer and magnetometer, and a very low frequency Whistler receiver. Students can collect and analyze data from any of these systems and relate their findings to the underlying physics. The focus of this paper has been to identify and describe a range of astronomy resources which can be used during the school day. Many of them are free or involve relatively modest cost. My aim is to foster exploration in this area and to encourage students and teachers to enjoy physics, perhaps becoming citizen scientists and contributing to relevant research projects.